Steve, could you close the door, please?
Yeah.
Thanks. Oh, somebody else. Last lecture we talked about the effect of viscosity on a sound wave. There's a loss of energy. It occurs as heat, and it causes the amplitude of a wave to decrease. Another effect that causes attenuation of sound is heat flow. We'll talk about that later in the lecture today, but first we want to talk about this what's called a phenomenological method. This is a word that's used in physics, and particle physicists love it. It means the situation is you want to do a theory, but you don't want to have to. You just want some results that you can work with. You don't want to have to derive everything from first principles. So that's what a phenomenological theory is. And an example is what's called the complex speed of sound. If we simply state, and I'll show this to you, if we just simply state, make the speed of sound complex, okay? And incidentally, I realized something here when I was looking over. I had plenty of time to look over these notes since we didn't have the class yesterday. This is not a matter, you know, we make the pressure complex and the condensation and just for convenience, right? And then we take the real part in the end. Well, we're hitting something different now. For example, in the effect of viscosity, we made the wave number. This is a genuinely complex quantity here. You only take the real part if you just want to find what 2 pi over the wavelength is. This is a real. We've actually generalized the theory here. It's not just a matter of simple convenience like we have been doing for complex quantities. And we can do. The way we can handle dissipation, as I'll show you, is we let C become complex, a genuinely complex number with a real and imaginary part. And what happens here is our dispersion relationship then becomes omega is equal to ck, where C is complex. And now, because omega has to be real, the way we're... So our primary interest here is in traveling waves, and there we think of omega as being real. When people deal with standing waves, they can actually make omega complex. For traveling waves, it's better to make k complex. So that's what we're mainly dealing with here, okay? So once we've hypothesized or stipulated this complex speed of sound, because this has to be real, k has to be complex. Otherwise, we're going to have a complex omega. Omega has to be real. So the bottom line, what we're going to find when we go through this simple theory here, is that by making C complex, we introduce an imaginary part in K. And what happens when you have an imaginary part in K? Do you remember that? That was a long time ago. It'll be here somewhere. When we have, this is a bold K. When we have, in addition to the real part, an imaginary part, we can get attenuation. Or we can get gain. You know, it depends on the sign. If the imaginary part is negative, we're thinking of alpha as positive here, then we get an attenuation. You can get gain in this theory too. What does that sound like to you? An acoustic laser? Yep, it's been investigated. It's only analogous to quantum mechanics. It's not the same operating principle as a standard optical laser, okay? But there are ways of getting a growth of a sound wave. And one of the interesting ones that I encountered years ago was under certain conditions, if you pass a sound wave through a bubble cloud, this is underwater and you have bubbles, the bubbles can actually serve 2 purposes. They can do 2 things to this sound wave. They can clean it up. If it's not a pure frequency, if it's kind of ugly, they can make it pure, you know, more pure frequency, and they can amplify it. amazing effect. So anyway, we're interested in this chapter, we're interested in this being negative, but the theory can be generalized to gain. You just change this sign right here of this, you're going to have gain here. Okay, so here's the treatment. Let's go through the treatment here. It's pretty simple. Here's our standard linearized thermodynamics relations. This is the normal speed of sound, real speed of sound. Okay. For linearized acoustics, there's this linear relationship between pressure and condensation. One of our basic equations here. When we let C be complex, we generalize this. This becomes generalized here. Now what's going to happen here, I'll tell you right now, is that the fact that this is complex, it's going to cause there to be a phase between these two quantities, or a time lag. And you know what that leads to attenuation, as we've seen. Now the other equations are, this is the linearized thermodynamics. Here's the linearized Newton's law, Euler's equation, F equals ma. Here's mass conservation, or the equation of continuity. It's also been linearized. So from these equations, if we assume a harmonically varying pressure, we get the Helmholtz equation. We've done this before. The difference here is that because C is complex, this coefficient here, which is, if you go through the theory, you find that the coefficient is omega squared over C squared. Because C is complex, now K becomes complex. So this is, we're going to carry on with this, but this is the method. Once we let C become complex, K will be complex. If we introduce a minus sign here for convenience, like we did before, you know what's going to happen here when you plug this back into a monofrequency, a traveling wave. You're going to get, if alpha is positive, you're going to get attenuation. So that's sort of the bottom line here. It's quite simple. To make the connection complete, once we've stated this, that K is given by a real part plus an imaginary part, C will be given by this expression. We can simplify here, omega over C. Now this is omega over K. This is the frequency over the actual wave number, 2 pi over the wavelength. This will be the actual speed of sound, speed of a wave. And what we're left with here, in this dimensionless denominator here, is this term right here, which is going to represent the attenuation or the gain. And we're going to be dealing here with just small absorption. Okay, so the wave is attenuating over a wavelength. The amplitude does not decrease much. Weak attenuation. That's often the case, but not always. So for weak attenuation, 1 minus a small quantity is 1 plus that quantity, standard approximation. So weak attenuation here means that the absorption coefficient is much less than the wave number. And this translates into the change in amplitude. The fractional change in amplitude over one wavelength is small. That's what this means. Okay, so again, the real part of C gives us the actual speed of the wave. The imaginary part gives us what we're interested in is the absorption. And you'll notice here we've just mathematically done this. This is not physics-based. We just hypothesized this complex speed of sound. It's useful because sometimes it can be very hard to calculate, as you will see, starting tomorrow. The calculations can be quite difficult. So sometimes people just really don't care. They just want to be able to put dissipation, attenuation of sound into a theory. So you can do it this way. And then you can treat this as like a fit parameter, right? You can treat this alpha like a fit parameter. Now continuing to nail this down, we already know, and I just pointed out to you in the previous lecture, when we write the complex k like this, a real part minus I times an imaginary part, where we're assuming this is greater than 0, we put that into our solution, and we get this exponentially attenuated wave. And this alpha is the absorption coefficient. So what we've seen here is that a small positive imaginary part of the speed of sound causes a weak attenuation, a weak decay of a sound wave. That's what we've seen here. That's a summary. That's sort of the whole point of this. Now we can go one step further. We actually did this in a homework problem. I think this is sort of needlessly complicated. What we can actually just jump to the bottom line here. Here's the wave impedance. Very important quantity, right? We use it all the time. It's the complex pressure divided by the complex velocity. In the past, it's been rho naught times the speed of sound. Once we've gone to a complex speed of sound, this becomes, you can show that the ratio of the pressure to the velocity is rho naught c. They're no longer in phase, right? Because of the complex speed of sound. Here's a derivation of this, but I think it's obvious that we have p over rho is equal to rho naught c, where c is the normal speed of sound. When c becomes complex, we just replace this with this becomes its complex value. So I don't know if it really needs to be proved here, but this is a proof. And c, as we've seen just on the previous page there, for weak absorption is 1 plus I times alpha over k. And then we do the Schwinger trick, remember? 1 plus a small quantity is the exponential of that quantity to first order. And the reason this is useful is we now explicitly see the phase between the pressure and the velocity. There's a phase difference. In this case, the particle velocity lags the phase. Okay, this is positive here. So the particle velocity lags the phase by this phase angle. Now, I don't know if you remember, but there's a homework problem we did last week, whatever day, Wednesday or Thursday. We handled this differently. We just simply wrote down that the pressure attenuates exponentially with time. That was a different perspective. And there we actually got the opposite. There the particle velocity, it leads the pressure. It's the opposite here. So what this is telling us is that this is a model here. This complex speed of sound is a model, all right? And there are different models here. There's no magical, this complex speed of sound is not like the only one. In fact, now that I think about it, we're going to encounter a third one in the problem set this week, I think. It's due to Stokes, which is interesting, because Stokes was around in the 1800s, probably early to late 1800s, I'm not sure. But before really modern acoustics, or just when modern acoustics was getting going, with people like Helmholtz, sort of early to mid 1800s. So the Stokes has a different perspective on this, a different way of getting attenuation in. So there's nothing unique about this. And this is kind of dramatic here. Here, whether the pressure leads the velocity or lags the velocity is not really important from a phenomenological point of view. You just need to get a lag in there. Okay. Now, while we're at it here, we want to look at something else that's practical here. You remember also from the same homework problem, we showed that because the pressure attenuates exponentially due to losses, the intensity is going to decrease exponentially. And there's a factor of 2 here because the intensity is proportional to the square. And the amazing thing about this relationship here is that it's only true to first order. It's only true for weak dissipation. Most people, including me, before I encountered this homework problem years ago, would think that, oh, it's exact. But it turns out not to be exact. It's usually not a problem in acoustics because we usually don't deal with severe attenuation. Usually the attenuation's weak, but it's not always. Okay, so now for the practical stuff here. The absorption coefficient here has, of course, dimensions 1 over length. This has to be dimensionless, of course, or this is meaningless. It has dimensions of 1 over length, okay? But that's not what people call it. People call it, they call the units here nepers per meter. A neper, N-E-P-E-R, not leper, neper. I don't know where this came from. Abbreviated capital N, lowercase p. Okay, so it's obviously a neper has to be dimensionless because we already have the meters in here. So you wonder, why do people use it? Well, think of radians. You know, radians are dimensionless, right? But we'll often talk about radians. For example, when you give a frequency, you know, so many, you can write it like this. This is, you know, like a certain, you can write it like this, but to be safe, oftentimes people will write it like this to signify that it's not cycles per second, just to avoid confusion, really, between cycles per second and radians per second. There's a factor of 2 pi there, which is huge. So a similar thing happens here. And it's even more important here, as you'll see, because we're next going to talk about the logarithmic. Often this is dealt with logarithmically, and we talk about dB, decibels. So these nepers are just something for clarification. It's dimensionless quantity. So this is a exponential decay. We can make it look simpler, and this is convenient, if we take the logarithm. So here, we naturally deal with the change in intensity level, or you can think of it as just the relative intensity level. We look at I divided by the initial intensity here and take the log to the base 10, and we multiply by what? 10 or 20? 10 because this is intensity, okay? It's just a scalar, it's just a convenient scalar. We're scaling things up, makes life convenient. So here's the intensity level here. Now this is the relative intensity level, or the change in intensity level. Because the log of, if I look at I divided by I naught to get this dimensionless intensity here, that's the difference of the log. So this is also the, you can think of this as the change in intensity level. It's equal to this, and we plug in our exponential attenuation. Now we got a little bit of a problem here, and you probably did this in high school, but not from this acoustics perspective. This is log to the base 10. This is an exponential. These are not inverse operations. Okay? If it were a 10, it would be an inverse operation. The log of 10 to anything is equal to that thing, because these are inverse operations. If this were a natural log, then they would be, but it's not. It's mixed. So the way we handle this, it's quite simple, is we convert this. Instead of e to something, we convert it to 10 to something. And that's something, we have to introduce a log e here so that this is the same as that. Now these are inverse operations, and we just get 10 times this quantity, which is minus 20 times this quantity. And now you can see that we have a relationship here. The intensity level decreases linearly with space. So if you look, instead of an exponential now, we look at the intensity level, it's increasing linearly. And this is really convenient. Acousticians who deal with this love it. They love the linear thing. So what they talk about there is you quantify this with so many dB per meter. This is measured in dB here, right? So for 1 meter here, I'm going to have a loss of so many dB. Down here, same. It's not true with the exponential, right? If you're looking at this, you're looking at just the intensities from space. You lose less here than you do here because it's an exponential. So it's a matter of convenience for people to go linear here. So an important quantity here is this slope. The slope is negative, and they call it A, okay? And it's technically known as the absorption loss factor. So you can see from our theory here that this A, the slope there, so many dB per meter, is given by 8. You punch this in, you find it's 8.7 times the absorption coefficient. So here we have this decaying exponential quantified by the absorption coefficient here. Here, we have it as a straight line. These are entirely different quantities, the A and alpha, and you don't want to mix them up because they differ by an order of magnitude. The ratio here is like an order of magnitude. So I'm going to edit this. We really shouldn't call this, I think, to be careful here, and this is why we shouldn't think of A as the absorption coefficient. Alpha is the absorption coefficient, okay? That's this right here. A is so many dB per meter. It's when we go logarithmic. So often results, as we will see later in this chapter, they're put in terms of, when you look things up, you usually find them in dB per meter. And you can see it's just more convenient because it's linear here. But you don't want to mix A and alpha up. That could cause a lot of trouble. Okay, so that's that section. Does anybody have any questions?
What would be the units of alpha?
Alpha has to have dimensions of 1 over length, so we call it Neppers per length.
Oh, yeah.
Okay, just like this, think of the radians. So that's how we do it, yeah. I know this is confusing, and it's this whole dB thing. You know, when you use dBs daily, you don't think about it anymore. But I don't do that. Okay, in my research, I tend not to use dBs. I just tend to use it to quote sound levels or something. I don't really deal with it very much. So it's kind of, you have to always have to, and I'm not the only professor here. There's others like this, okay? So we always joke about how we don't like dB and we have to stop and think about dBs because we don't use them every day. So I don't want you to think that the use of dBs are simple, but once you get into it and you start using it, you know, which is necessary. This is much easier when if you're dealing a lot with attenuation of sound, it's much easier to deal with this linear relationship than the exponential relationship. But there's a price you got to pay, right? Like with everything. Yes. Absolutely. Oh yeah. So we've already calculated alpha due to viscosity, due to shear viscosity, right? Now we're going to calculate it for thermal losses. And it's not obvious why there are thermal losses, okay? We're going to go through this calculation. We'll finish it today. It's actually a kind of a difficult calculation, as you'll see. But it's good to see. You learn a lot from it, I think. It's a good experience. As I've said before, it builds character, okay? But it is difficult. But first of all, let's look at the basic physics here. Here's a sound wave, and you can think of this as a traveling or standing wave. It doesn't really matter. In space here, and there's a temperature variation because sound is adiabatic. When there's a compression, this is a compression right here. It's hotter, and it's colder here. Well, the fact that it's hotter here in this region, and colder here and hotter there, there's going to be heat flow from the hot region to the cold region. You know that. It's got to be. Right? Now, how big it is, well, that's a whole separate issue. But in principle, it's there. What happens when heat flows here this way, and it's going to flow this way? What happens to the amplitude here? It goes down. What happens to the amplitude here? Well, I don't know how to answer that. It goes. Who said that? What'd you say?
It goes towards zero.
Yeah, right. That's a safe way of saying it. The amplitude, you know, looks like it's going up here, but it's really the amplitude, which is is decreasing. So we can see here that due to heat flow, a sound wave is going to attenuate, and we call this usually a wash. That tends to wash out. Think of a propagating wave here. As it propagates, because this heat is going to flow this way and this way, and therefore, by energy conservation, reducing this amplitude and also reducing this amplitude. Because heat's being added to the cold here, it's going to reduce the amplitude. It's going to cause an attenuation. It causes a kind of washing out of the wave. So the problem comes in calculating this, all right? So that's what we're going to do for the rest of the lecture here, is to calculate this effect. And it's useful, I'll tell you right now, that typically for gases, it's of the same order of magnitude as viscous losses. So we got to include it. For liquids, I think it tends to, we'll talk about that later in this chapter, but I think I can't remember. But anyway, I know that it's well known that for gases, as where we use the ideal gas law, it's comparable to viscous losses. And in fact, we're going to consider, our calculation here is going to be, we're going to assume an ideal gas, all right? And it's a difficult enough calculation with an ideal gas. However, you can do it in general for any fluid. And it turns out you get the same result if you phrase that result in a particular way, a standard way. And I'll talk about this. And if you ever need to know the derivation for any fluid, it's in Landau-Lifshitz fluid mechanics, like just about everything is regarding fluid mechanics. Great book. Have I mentioned this before in this class? I think I have. Yeah. So, all the acousticians I know, physical acousticians, they all have Landau-Lifshitz fluid mechanics because they treat acoustics as a special case of fluid mechanics. There's a lot of acoustics in that book. It's really useful. It's very dense and compact, but it's just, I look at it all the time and refer to it when I write papers all the time. Okay, so the first thing we need to do here to kind of set things up is forget this effect for the moment. We just need to come up with a relationship that we're going to use later. So we're going to consider the usual sound, adiabatic temperature variation, and no acoustic losses due to thermal conduction here. And this is, like I said, just to get a relationship here. So let me remind you, everybody knows this from high school. This is one of the things that I've noticed students remember from high school, right? So, which is good, I guess. This is the ideal gas law. We know this is for an ideal gas, this is going to be true. For sound, we know that sound is adiabatic. Never really proved this to you, but I'll discuss a little bit later how it can be proved. When there are these compressions and expansions, there's very little heat flow. Okay? So that means, I guess now that I think about it, that means two things, doesn't it? It's not isothermal. So when there's a compression, if it was isothermal, when you compress this, heat would flow, right? It's not like Newton thought. Sound it's not isothermal, it's adiabatic. And now we know that the fact that it's adiabatic, that's going to tend to cut down on the attenuation due to thermal processes, right? Because there's not much heat flow there. So it's going to tend to be a weak effect here because sound is adiabatic. So in this case, for an adiabatic process in thermodynamics, the pressure times the volume to the gamma power is a constant, where gamma is the ratio of specific heat, Cp to Cv. So for fluids, for fluid dynamics and acoustics, we go local. The velocity, and this is not a good variable, we go to the density. So we get that the ratio of the pressure of the density is proportional to the temperature. And here it's going to be P over rho to the gamma is proportional to is going to be constant here, okay, when we go to rho instead of dealing with the volume. Now it's convenient here, we're going to find it's convenient later in the derivation here, to express this information here in terms of temperature and density. And that's very easy to do. We eliminate the pressure here because the pressure is proportional to the temperature times the density. So when I substitute that in here, I see that the temperature over rho to the gamma minus 1, right? Because we have this, when we substitute P in here, we have T times rho. So this is going to be a constant. We can evaluate it in equilibrium. Okay, when there's no sound wave, we get this. And now the next thing we do here, setting this up for later usage, is we take a differential of this. And we just look for small changes about equilibrium. For small changes about equilibrium, we take a differential of this. This quantity will change and this quantity will change. This is gone, okay? And because we're just interested in linear variations here, when you see this quantity, wow, when you see this, we already have the variation in equilibrium to first order, we just set this rho equal to rho naught. The difference between this and this, which comes up, this is going to come up in our derivation here when you take the differential. The difference between these two is higher order. So for linear variations, we just evaluate it in equilibrium. So here's what we get. When you take the differential, we get this. This relates for sound wave temperature change and condensation. Here's the condensation, the fractional change in density. So we're going to use this later, okay? And it's linearized. It's linearized. It's a linear relationship. Okay, so we need to deal with heat flow here, right? We've seen that qualitatively, this amplitude will tend to get washed out due to a flow of heat. What dictates the flow of heat? Well, it's a very simple equation here. Heat flows when you have a temperature gradient, right? So if you have a hot region here and a cold region over here, heat's going to flow this way, right? The temperature gradient, so you need a temperature gradient. So mathematically, the first thing to recognize here is you're going to get heat flow if you have we're neglecting convection here, of course, okay? That's another way to transport heat. We don't have convection here, okay? Remember, it's in acoustics, linear acoustics. You'll notice here, so you're going to need a temperature gradient. Which way does the temperature gradient point? It points this way, okay? So we have to have a minus sign in here. So the important quantity is how do we quantify heat flow? Well, the standard obvious thing to do here is it's heat or energy per unit time per unit area. So that's called the heat flux density. It's very much like the mass flux density that we talked about for the equation of continuity. Here, instead of mass, it's heat. So the heat per unit time per unit area, it's natural to guess that it will be proportional to the gradient. If you double the temperature gradient, you're going to double the heat. This is what you would guess, and it turns out to be highly accurate. So the heat flux density will be proportional to the gradient of T. We need to put a minus sign here because it's going in the opposite direction. And then it'll vary from one substance to the next. So we put a quantity we're going to call kappa there. And that's called the thermal conductivity. It varies from one medium to the next. Now, this heat, the energy is going to go up here. When heat flows here into a region, and it doesn't flow out, okay? When there's a net flow in, the temperature is going to go up. So we need to quantify that. So how do we do it? Well, we can actually do it. We can it's analogous to mass conservation. So you remember the equation of continuity. Basic equation of fluid mechanics is given by this. This is the mass, the density, the mass per unit volume. If I want to know how it's changing at a point, the only way it changes is if mass comes in, goes out or comes in, because mass is considered. So this is the mass flux density. And if you have the same coming in as you have going out, if you have no divergence here, then this is not changing. But it's going to change, its rate of change will be equal to minus, as we showed earlier in the course, the divergence of the flux density. So when you have a change in this, you're going to have a change in density. So the same thing happens here. We need to to find out how the heat or energy is changing in time. We'll let Q be the heat per unit volume. It's analogous to the mass per unit volume. The rate of change of that is going to be minus the divergence of the heat flux density. So I take minus the divergence of that, I get the Laplacian with kappa here. So this tells us how the energy is changing in a volume due to heat flow. Now, looking ahead a little bit, why is that important? Where is, in our case, what we're interested in, where does that energy have to come from? The sound wave, right? So the amount that this energy goes up here due to this heat flow, this generation of heat, is going to be identical to the amount that it goes up will be the amount that the energy of the sound wave goes down. That's how we're going to be able to calculate, to quantify the attenuation of a sound wave due to this heat flow here. Now I want to point something out here. We've talked a little bit about this before. We're just one step away from a famous equation called the diffusion equation, which occurs all over the place. It even occurs in quantum mechanics, although it's complex. Okay, so the diffusion equation, some of you have probably heard of this before. We're almost there. And we get there in a natural way. If you want to deal with this equation, you've got two variables here, so it's natural to try to come up with one variable. Right? We've seen that before in acoustics. We usually use the pressure for linear acoustics. So we can eliminate Q here. And the way we can do it, it turns out, is it's related to the specific heat, the heat capacity, constant pressure, the density, and the change in temperature. The important thing to notice here is that the temperature is going to go up proportionally to the heat. Right? And here's the quantitative relationship. If you take this and substitute it into our equation here, equation on the previous page, you get this. And again, this is a famous equation. In our case, we have the temperature here, but it can be in just about anything here where things diffuse rather than propagate, whatever this quantity is here. In our case, it's the temperature. You'll notice it's a partial differential equation. It's first order in the time, and it's second order in space. Okay? So it's not the wave equation. It's fundamentally different. There's no propagation here. We call it diffusion, and heat diffuses. So the coefficient here is called the diffusion coefficient. And in this case, for our case, for heat flow, it's given by the thermal conductivity divided by the specific heat and constant pressure times the density. And it varies from one material to the next. Anyway, I'm pointing this out. Well, I'm going to make another statement about this at the end of the lecture. So I just wanted to point it out right here. Okay, so if you look in KFCS, the next thing here is to make progress on calculating how a wave attenuates due to heat flow. They plop down this identity here. So this is a vector differential identity. It's a very unusual one. Usually when people want to find identities like this, they open up their electromagnetism. Physicists open up electromagnetism. They look on the inside cover of an E&M book. Engineers probably go to a fluid dynamics books. Very similar. The identities are the same. And I don't know if you often see this. I should look and see if this one is there. This is very unusual, but we need to use it here because we're dealing with the Laplacian, and we want to convert this to something we can deal with, and we can deal with the gradient of t, and we're going to get that. Looking ahead here, we're going to get that from here. We can convert this into a gradient. So we need to use this identity. It's not simple. And in fact, I think KFCS actually make a mistake. I mean, they get the right answer, but I think their logic is flawed. Okay, I'm not completely sure. But here's what they say. They say, okay, this is an identity. This holds actually for any scalar. It's an identity, which means it holds for any scalar function, t here. Okay. They say if we, for small oscillations about temperature, we have the small temperature change. They say the second term averages to 0 for small amplitudes. This is just going to average to 0. The problem here is that when you deal with acoustic energy, it's quadratic in the field. It's proportional to the square of the field. So I think it's really dangerous here. I don't think, they're using a linear acoustics here to argue that this term is not going to contribute. And I don't think that's right. I'm not sure. But what I did once, I remember, is you can calculate. You can go to second order. Instead of go beyond the first order, linear acoustics, you can go to the next order up and calculate this. And it happens to vanish. I don't know. I don't know why, but it happens to vanish. So because of that, we can neglect it here. So we're going to be able to replace the Laplacian in t with 1 over t times the square of the gradient, which is really convenient here. Okay, so energy conservation here. We've generated heat. We've got this thermal energy that's flowed here. And it has to come from the sound wave. That's the only place where it can come from in our case. It's the only possible source. So we have to have energy conservation. The rate at which, we're going to let script capital E here be the time averaged acoustic energy density, energy per unit volume. It's going to be going down, right? And the thermal energy will be going up by the same amount. So remember, we have this heat per unit volume here. It has a rate of change. We're going to integrate over little volume and these are going to be time average quantities. That's all we're interested in is time average. So we take this dq dt, which we know in terms of the Laplacian. We replace the Laplacian with the gradient divided by t, right? We use this identity with the square of the gradient divided by t. And here's what we get. Okay, now this looks complicated, but we're about to make it look really simple. The next thing we do is we use our relationship that we derived in the beginning here between, that relates the temperature change to the condensation change. Now you might say, wait a minute, we derived that assuming no losses. So how can we use it here? What's the answer to that question? The students have trouble with this. I don't expect you to know, but it's like the basic idea of perturbation theory. The energy of sound wave is going to be going down by this amount, right? And we're assuming weak losses here. So in this expression, we're free. In fact, we actually have to. We're free to neglect dissipation here. This is a dissipationless result that we got here. We actually, to be consistent, because we've made approximations getting here, we have to use it here. So I know this sounds confusing, but I just want to get it in your heads because as you go on, you start to do more and more perturbation theory. This is an essential thing. You know, we can't solve anything. In the real world, we can't solve anything exactly. People use perturbation theory all the time. So we've got this relationship here telling us how the acoustic energy is going down. And it's given by this. This is going to be relatively small. Okay? So here, we're free to use results neglecting dissipation. If we included them here, it would generate a higher order, something that's small. It would be a higher order effect. So that's why we can get away with this. We use this. Oh, and I can turn this into a gradient. I can just divide by a distance. I'm free to do that. And I can get this. We substitute that into there. Okay. And now, when you do that, and we're going to deal with a traveling wave here. And we know, looking ahead, we know the amplitude is going to be going down. So this is going to be a function of time. It's going to be going down slowly, relatively slowly, over a wavelength. We made that assumption here. We get this equation. And now we can make this look much better. Okay? And here's how you do it. If you stare at this, you'll say, p squared. Well, that's proportional to the energy density, right? In fact, here's the relationship for a traveling wave. Here's the energy density. We derived this earlier in the course, right? If we substitute for p squared into here, we're going to get this first order differential equation in E. And here's what it looks like. Okay? It's a bunch of constants here. There's a minus sign. If we didn't get a minus sign, that'd be exciting. We'd have an acoustic laser. Okay? And you know, people have worked on this. It's obvious, right? But you've never heard of it probably. Maybe some of the Newark students have, I don't know, or distance learning students. Hasn't really become popular, but people have, there are different acoustic type lasers that people have worked on, done research on. And that would be appropriate, you know, with a plus sign here. But we're interested in attenuation, so we know we have to have a minus sign here. You can see that it has to be proportional to E, you know, because this is p squared. And all the other stuff we lump into a constant here. And it's convenient to put a 2 and a c here. And you'll see why. You'll see why in just a moment here. Now, This is a constant, right? Everybody can solve this. What's the solution to this? Decaying exponential, right? Okay. So, by the way, this alpha here, this alpha sub k, this will end up being the absorption coefficient due to thermal losses, due to thermal conductivity. That's what the kappa there is for, thermal conductivity. It's given by this expression. That just comes from the previous expression. Now, we got a little bit of a problem here. It turns out that what we're seeing here, what this is we're actually following the wave. It's not obvious, but what this represents is following the wave. And this is how the energy would change in time. We can convert it to space, okay? So it decays in time like this. The wave is moving at speed c, so we can convert this time derivative to a spatial derivative just by this ratio, just by putting a c in here. And when we do that, when we make that replacement, what we find, what you find then is that the amplitude, the c's will cancel here. That's why we had to introduce a c here. All right? And the energy will decay as e to the minus 2 alpha x. Oh, I can't believe I did this. This is wrong. I have intensity here? Yeah. Okay, so that's good. we should have a 2 here, right? Amplitude will decay like that. So that's why we introduced this 2 here. So we found that the amplitude will, due to thermal conductivity, the amplitude of the acoustic wave will decay in space as e to the minus alpha c. This is the absorption coefficient for thermal conductivity. Now there's one more step here. For an ideal gas, this is thermodynamics, you can show that the heat capacity at constant pressure is given by this expression in terms of the temperature, okay, the ratio of specific heats and the speed of sound. This is a thermodynamic identity. So we do that here. It's not obvious, but I'll tell you why people do it. We get rid of one of the powers of gamma minus 1. Okay? And we get rid of the equilibrium temperature. So this identity allows us to express this like this. So why do people do that? It's not obvious. The reason they do it is Landau-Lifshitz. Well, Landau-Lifshitz weren't the first to do this, but it's just the standard reference. It turns out, amazingly, that this form of the answer, this is true for an ideal gas, right? This form of the answer is true for any fluid, amazingly. Which is, of course, useful, especially for us, because we want to deal with losses in water, right? Not an ideal gas. So if you're interested, you can look at Landau-Lifshitz. It's a very this derivation wasn't simple. Theirs is less simple, okay? More mathematical. But it's in there. Okay, now just some quick items here, I think. Right. So here's our, put a box around, this is an important relationship. Here's our thermal absorption coefficient. The first thing you want to notice here, I think, is that when there's no thermal conductivity, when you're dealing with a substance that just is an extremely poor conductor of heat, what's the absorption coefficient? 0, right? So extremely small. That's because you don't have any heat flow. This is all related to heat flow here. So if you have no heat flow, you're not going to cause any absorption of sound. That's one thing. Oh, you'll also look at this, the elephant thing, omega squared. It's always true that it seems to be always true that at low frequency, these absorption, no matter what kind of absorption mechanism it is, it's going to go like the square of the frequency. The other thing that comes out and hits you here is this gamma minus 1. Why is that there? So in other words, when gamma is equal to 1, we have 0. What does gamma equal to 1 correspond to? Do you remember?
Isn't that the specific capacity over the, or for constant pressure over constant volume equaling 1, so they're equal?
Yeah, the heat capacities at constant pressure and constant volume are equal. It means when you compress something, the temperature doesn't change. So that's what gamma is equal to 1 means. We've talked, and you can look back at that if you don't remember. So in that case, we have the sound wave of compression. If its temperature is not going up, there's not going to be any heat flow. So we got to have that there. We get zero absorption. It's got to be there, and it's there. So on final note here, there's a relaxation time. Associated with these losses is a relaxation time. Remember, shear viscosity, if you have a fluid and you make a sudden change in the fluid like this, it won't, due to viscosity, it won't respond instantly. Okay, this is beyond inertial effects. And there's a viscous relaxation time. There's also a thermal associated with the loss mechanism here. There's going to be a thermal relaxation time. And I'm going to edit this. You can get at this from the diffusion equation if you wanted to prove this. KFCS stated without proof, but if you want to prove it, you can do this. And our whole theory here is true for small absorption, you know, alpha small compared to the wave number. And from the relaxation point of view, it means the relaxation is really fast, right? The relaxation time is really short. And technically what that means is short compared to what? Well, compared to the period. So our theory here holds. We can look at it from this perspective, for the loss perspective, for the absorption perspective. From the relaxation time perspective, it's equivalent to this. And one final note here, and we talked a little bit about this before. What do we mean? So what we mean by short relaxation times, we mean omega. Strictly, we mean omega times the relaxation time is much less than 1. That's what we mean by short relaxation times. You might, so you can think of it as a low frequency limit, relatively low frequency compared to in general, where this could be comparable to 1 or even greater than 1. You might think if I have a low frequency sound wave that it would become isothermal because there's plenty of time for thermal equilibration to occur. Right? And I think we might have talked about this once before, many weeks ago. Why is that argument not right? What is that argument missing? I've got a low frequency sound wave. It's got compressions and expansions. It's hotter, it's colder. If it's going to low frequency, it seems like there'll be plenty of time for the heat. It seems like it should be isothermal, not adiabatic. What's wrong with that argument? What happens as I go to low frequency? What happens to the wavelength? Heat has farther to travel. And it turns out, because the diffusion equation is first order in time and second order in space, that wavelength effect beats it out. So the fact that the heat has farther to travel, yeah, it has more time to do it, but more severe is the fact that it's got much longer to go. So this is one of the things we learned from the diffusion equation, which I didn't prove to you. The reason we know sound is adiabatic, which we did not prove, is from the diffusion equation. It's from the diffusion equation. When you plug numbers in there, you find in typical cases that the heat just doesn't have, it doesn't have the time, or there is too much distance for it to equilibrate. Okay, so tomorrow the next lecture is tomorrow, right? All right, okay.